Today we have Tristan Tomilin. He's a PhD student in the data mining group in the Department of Mathematics and Computer Science at the Technical University of Eindhoven since 2001. His interests span basically all of RL, including continual learning, multi-agent systems, safe RL, and generalization. And his research is categorized by a focus on robust, reliable, and meaningful simulation environments. So I think we can maybe ask him a lot of questions at the end or during why he's interested, like what drove him to be interested in creating these sort of environments. But he's worked on a lot of interesting environments that he'll talk to us today about. And his main topic today will be about benchmarking pixel-based RL and how we can use this to test things like continuous RL and generalization. Tristan, super excited to have you. So if you can share your screen and yeah, start when you're ready.
Yes. Okay, screen should be visible now. Yes, thanks for the introduction, Caleb, and the invitation. Perhaps the only correction I would make to the introduction is that, in fact, I have not started the PhD from, as much as I love the PhD, I have not started at 2001, but at 2021. So minor adjustment there. So in fact, that's not been 20 years. But other than that, yeah, first and foremost, I think it's a great honor to share the stage here with many of the famous people and speakers that you've had on the talk before. So happy to share the stage and very much excited about the talk. So I guess this one will be a bit more lighter, on the lighter side, and less mathematically involved. So I preemptively have to disappoint those who are looking forward for something more complex and involved. So I'll talk about more about environments and benchmarking within the realm of reinforcement learning. So without further ado, as the convention goes, I'm focusing on the wrong screen. So I'll start with giving a bit of a background and the motivation for why we want benchmarks, why is it important, what are good benchmarks, and what we care about when we design benchmarks, and also how can we incorporate video games within the research of RL. And after that, I will discuss 3 of our projects within benchmarking on generalization, continual RL, and safe RL. I'll first start with a bit of background. So to make proper things and make things well and make great things, we need proper tools. If we have proper tools at our disposal, we are generally able to make things that are well functional, usable, look good, feel good, and so forth. If the tools at our disposal are inappropriate and dysfunctional, then often the things and products we end up making might not suffice or be that functional or well usable. So in the broader realm of reinforcement learning or AI research, on the one side of the spectrum, we have the theory, the theoretical foundation. And on the other side of the spectrum, we have many of the great advancements in practical applications that we've seen in the recent years. So the big question is what lies in the middle ground of this? And I'm sure there's a lot of things behind this question mark, and unfortunately, I will not be able to fully incorporate all of that, what does lie behind the question mark. But one thing I can say more or less for sure is that we definitely need a good set and suite of proper tools at our disposal to conduct research. So that being said, we already know there's a lot of famous useful libraries out there that have baseline implementations of reinforcement learning methods and so forth, where we can obtain some models that we can use in our research. But often what is lacking is certain environments that are narrowed down or for a more domain-specific setting for these simulation environments and benchmarks. So we often see that researchers need to adapt and modify the environments themselves in a more ad hoc manner, whether it's a multi-agent setting or a robotic setting or whatever the domain is. We'd rather we could say this effort can be used better, and it also often leads to reproducibility issues if everyone to test out their model or method in a particular setting, they design their own sort of experimental apparatus, if you will, of designing an environment and modifying it. So, and with when designing benchmarks, there are often certain challenges we face that are important to consider. One of which is the standardized metrics. So if we want to measure something, we want to measure it according to the same principles and premises. There's often a problem with the computational requirements, as not everyone is Google or OpenAI. So also we want to have environments and benchmarks that are feasible to run on lower budget settings for university students or so forth. Further, the installation and usage of certain environment suites and benchmarks are often relatively complex. And we can probably have noticed that often there's a lack of documentation and the code is written in a poor manner. So these are all things to address. And lastly, also the absence of baseline evaluations. It's way easier if we already have a set of baselines to compare against. So with that being said, I'll now move on to why we care about video games in particular in the scope of reinforcement learning research. So video games, as we know, are effectively ready-made simulation environments, right? They're already there. They were initially designed for a different purpose, but they do create a good setting for training RL agents, and for good reason. Namely, they provide many complex problems that are difficult to solve both for humans and for agents alike. We can run them in a safe and controllable setting. So we wouldn't want a safe self-driving car to drive into a wall because an activation function misfired or whatnot. So this all benefits to their usage. And further, they also facilitate this canonical reinforcement learning loop that we've all seen, where we have an agent performing actions in the simulation environment and obtaining the next state and a associated reward with that. And crucially, we can learn from pixels because this correlates strongly with many practical real-life applications that we have as well. So effectively, anything that's navigable and it has a camera attached to it on the premises also perceives the environment in a similar fashion. So learning from pixels in these environments has a lot of leverage for more real-world applicability. So for these reasons, video games in particular, have been used a lot for AI research and reinforcement learning. And Doom in particular is one of those environments that is widely known and has widely been used, and even recently, and also for many good reasons. As the meme goes, it can be installed on very many different platforms and it's very lightweight. Although it can be argued that it's very far from reality, it nevertheless mimics this 3D environment where the agents can navigate through and interact with. And the perception within these environments is similar to how us humans perceive the world from this embodied egocentric view. And it facilitates very high speed off-screen rendering up to 7,000 frames per second. And very importantly, we can customize the scenarios and their difficulty alike. So with that being said, I'll introduce the first benchmark we've created on generalization. And to start off with our first, talk a bit about what we mean under generalization, or at least in the scope of this benchmark. So as humans, if we learn a given task, we are often able with little effort to use the knowledge we've gained to generalize to a somewhat similar task without any additional learning or fine-tuning. And in a similar fashion, if we learn many lower level easy tasks, we can extrapolate this knowledge to generalize to more complex tasks. However, when it comes to autonomous agents, if we try to naively utilize the same setting in which we teach them to perform any given task, and we try to have them generalize to a very similar task, we're quick to realize that this might not be too easy to do, and naively often does not work. So similarly to the example, if we try this in the Doom environment that I mentioned, then if we teach the agent to perform a simple task in this environment and it learns to do it reasonably well, if we try to generalize that to a slightly different environment where the objective is the same and the dynamics of the environment is the same, but the only thing we change is the background colors of the textures and the floor and the walls. And that is already enough to fully derail the agent, and the policy it has learned is not sufficient to perform this task any longer. So having that in mind, we then introduce this generalization benchmark that is based on the Doom environment. And we have these 4 tasks with all very different objectives. And the goal is then to generalize to modified inversions of these tasks within the same task of the environment. And we also measure a notion of difficulty, which is then determined by the number of modifications that a particular environment has. So then the question is, can we modify the environments? So one thing we can do is change the layout of the map. And we can also change the visual rendering of certain items or entities within the environment. We can change the items and entities themselves. We can change the textures, as you already saw, of the surrounding areas. We can change the view height of the agent, which creates a certain shift in its observations. We can add obstacles to the environments, which, for one, act as distractions or just distractive objects, but also impede the movement and the navigation of the agent. And lastly, we can change the size and shape of the environments. These are all separate types of modifications we can introduce. So then we can ask, can we create increasing difficulty by combining these? So what we try to do is, taking this task as an example, we define the default environment as level 0, having none of the modifications applied. And if we apply a single modification, we obtain a level 1 environment. And if we combine 2 modifications of different types, we can obtain level 2 environments, and then so forth. With 3 modifications, level 3, and finally with level 4, we just combine all of them. And what we do in our experiments here is allow training on the easier level 0 and 1 tasks, and then evaluate the trained policy on the higher level tasks. And we run a few famous simple reinforcement learning baselines. And the main thing we can notice is that the performance tends to decrease as the difficulty level gets higher. So if we aggregate the results within a task, within a level across the tasks, we can see that indeed the higher levels have much lower generalization performance, meaning then that just by combining these different types of modifications, we are able to present a more challenging setting, and therefore the generalization capability of the agents is reduced. So with this, we provide a benchmark suited for generalizability. So then we ask the question, what if we do allow training on new tasks, and we arrive at the realm of continual RL. But perhaps here, if there are any questions up to this point, then now would be a good time to make a short pause and take them.
I think we have one hand up and one question in the chat. I'm not sure if the person asking the question in the chat wants to ask the question, or I can also just read it out. I'll just read out. Do the modifications make the Doom environment always more difficult, or may it simplify it as well?
Mm-hmm. Okay, so I would say in some scenarios, it definitely makes it more difficult. For instance, if we introduce those obstacles, then it's clearly harder to navigate the environment. But in other terms, what we're interested in, that the modification, whether or not it makes it more difficult, it's still visually diverse, like the textures, for instance. And I'm now thinking of an instance whether it actually makes it easier. I don't think any of the 7 or 8 ones that I introduced, that because the dynamics of the environment stay the same with almost all of them, except for the for the obstacles one. So because the dynamics are the same, that also means inherently the task is the same. So it's just the visual disparity that is introduced if we train on an environment and evaluate on a different one.
Okay, cool. Makes sense. We also have 2 hands up. I think first was Sam.
Hey Tristan, good to see you,
Good
man.
to see you.
Yeah, I had a question. Like, maybe you mentioned it and I didn't hear, but how do you assess difficulty, or how do you measure that like one environment is more complex than the other? Is it just the RL agent performance, or do you have like a way to do that?
Yeah, that's a good question. So there's no clear measure apart from the fact that we simply combine the modifications, right? So this is the only way we define it. So you can see that in the experiments, there are often, in the results, there are often instances where, for instance, the performance on a level 3 task can be even better than on a level 2 task, and similarly with 4 and 3, right? So it's not always necessarily the case that the higher level here is more difficult, but the crucial part is that if we average them all together, then indeed we see this performance disparity, because in the modification types are all very different. So their incremental the incremental difficulty they add might be very diverse. But if we have enough environments and we evaluate on all of them and then combine the results, then we can indeed have a more then we can have a good measure of like complexity.
And so this performance you report, it's the you train on level 0 and 1, and then you evaluate on level 2, 3, and 4,
Yeah,
and you see like this.
this is only the evaluation performance that I've shown here.
Would you say that, like, in terms of the sort of distribution of trajectories you will see as you increase the level, they are more and more out of distribution as well, or like it's only complexity? Because sometimes, you know, like you see RL agents, they will really struggle with something out of distribution, but not necessarily like something we would us see as more complex, but just that is like further away from their training set. So I was just curious of the relationship between the two.
Okay, yeah, that's a fair point. I think, yeah, when I mentioned this, I mainly I referred to it as complexity, but indeed, we can also call it as just the distributional shift in terms of the observations it gets. So indeed, it's the same thing. It's not always necessarily that there's inherent complexity in the environment, but we care more about this visual disparity. So it's exactly what you said. The complexity arises from the notion of this mainly visual disparity. Yeah.
Right. Yeah. That's that makes sense to me. Yeah. Okay. Thanks a lot for answering that.
Yeah. Thanks for your question.
Okay, I think there was one other hand up, but we can skip it for now and continue. And then if people have questions, I'll just let you know.
Great. Then in a similar fashion, I'll start off with some background. What do we care about in continual learning and what we consider important to measure? So again, as humans, if we learn tasks sequentially, then learning sequentially, meaning we learn a task and then we move on to a new one and we no longer have access to essentially learning the first one. Then at the end, when we've sequentially learned a sequence of tasks, where relatively with a relative ease, we can recall and perform the task that we learned perhaps at the beginning of the sequence. So we do not lose this. We rarely, in a quick fashion, we rarely lose this capability. However, with AI agents, this capability does not exist, because the moment we switch to a different task, whenever we perform a policy update due to the rollouts of the information we've gathered in this new environment, our the gradients we've accumulated will be pointing in a very different direction than they probably were for the previous task. So that's why neural networks inhibit this phenomenon known as catastrophic forgetting, and we very quickly forget the task we not too long ago learned. So another important phenomena in continual learning is forward transfer. So to understand this, picture that when we are trying to learn the fourth task in our continual learning sequence, then perhaps we can leverage the knowledge and competencies we've gained from learning the previous task, and we can actually learn this fourth task more faster, more efficiently, and therefore build a more fancier car with the same amount of time of learning. And we can refer to this as transferring knowledge forward. And if we can transfer it forward, perhaps we can also transfer it backward, meaning that after we have learned a sequence of tasks, if we now recall an initial task we learned, perhaps the tasks down the line of the sequence have taught us something more about the initial task. So although we didn't have access to it and we didn't learn anything explicitly about it, we might have better evaluation performance on an initial task just by learning future tasks. So in essence, we transfer knowledge backwards. So having said that, we, in a similar fashion, introduced a continual learning benchmark, coincidentally also on the Doom environment, which this time we have, we've also modified the environment visually, and we obtain a cross-domain sequence. And a more interesting setting is not only modifying it visually, but also introducing new objectives every time. So every next task in the sequence not only has different visuals, but also a new objective. And we'll refer to this as the cross-objective sequence. So we can shorten these later experiments as CD8 and CO8. And one important thing that we can notice is this task interference, in which if the agent on the third task learns that it's a good idea to simply shoot at everything that is red, and this will be a good policy because the targets that it has to shoot are indeed red. But if we now use this policy on the sixth task, then that will no longer work very well because more or less all of the surroundings are of the same color. So these tasks sort of visually interfere with each other. And in terms of objectives, they can also interfere in this lower sequence in which on one of the tasks, the agent has to flee or move away from the enemies, and in the other one, it has to sort of seek them or hunt them down. And moreover, because these tasks are relatively different, and so are their objectives, and then the success metrics are therefore different, we have to have a notion of a unified success metric, which we define between 0 and 1 to have an equal sort of performance across the tasks. So then we again evaluate some continual learning baselines on these environments, which fall into these 4 categories of regularization, architecture, rehearsal, and naive. And the final fine-tuning one is simply just continuing training without doing really any continual learning. I won't go too deeply into how these work. Just keep in mind that there are often these 3 main categories how continual learning methods are often categorized in literature. And they're all based on the soft actor critic method to ensure like a fair sort of foundation for comparison. And the main thing we measure is simply the average performance. So our goal here is to have the agent have good performance on all of the 8 tasks, but we only train them on 1 task at a time. So if they've managed to, after learning all of those 8 tasks sequentially, perform well in all of them, then they will have a very high average success, which is near 1, given, for instance, for the the blue and orange curve. And we do observe a very a great disparity of performance across the methods. So for instance, AGEM with the red curve almost immediately forgets the task it has learned. And that's why it has this bumpy curve and it stays very close to the lower end of the figure. So numerically, we can simply measure this by averaging the scores of every time step of every task. And from the results, we can see indeed that Pacnet and the colonic stack method perform the best in terms of under this metric. And when we talk about forgetting, we can visualize this by plotting each task separately. So with the case of AGEM that did not have such good performance, we can also see it here, in which almost right after it has learned a task and has lost access to that task and is being trained on another one, the performance on the previous one plummets. So it always forgets the task that it has been trained on. Whereas if we compare this with a method that performs a lot better, then we can see that it inhibits barely any forgetting. After it has obtained a reasonable amount of performance after training and converged, it has almost fully managed to maintain the same performance until the end of the sequence. So we can measure this by simply subtracting the performance at the end of a task from the performance at the end of the sequence. So if we look at the results of this, we can see that the regularization-based methods such as L2 and EWC have performed the best in terms of forgetting, or at least are one of the ones, because that's essentially all they're trying to do is apply regularization to not forget what they have learned. And you can also notice that some of these values are negative. So if we have negative forgetting, that means we have positively transferred knowledge backwards, meaning that, well, the agent can have technically better performance at the end of a sequence than it had at the end of a given task. But however, these values are very low, so we couldn't really confirm that we noticed much positive backward transfer. And finally, forward transfer visualized by plotting the evaluation curve of a continual learning method and comparing that with the soft acrocritic baseline, which is simply directly trained on the environment itself, just individually and separately. So good forward transfer means that we have learned something from initial environments that we can now leverage and learn new environments faster. Perhaps in this 3D Doom environment, we have learned that running headfirst into walls is not a good idea and probably does not lead to high rewards. So that's why it's able to learn newer tasks faster and have positive forward transfer. And we can measure this by calculating the areas under the curve for both the continual learning method and the soft acrocritic RL baseline, and then simply find the difference, the normalized difference between them, and then we can have results for the forward transfer, in which interestingly the fine-tuning method happened to perform the best at. So going further, we compared the resource consumption of all of these methods, and they more or less remain the same apart from the perfect memory method, because perfect memory, all it does is just memorize everything. So all of the experience it has gained from the past tasks, it simply keeps it in the replay buffer. And of course, that leads to a very high memory cost, but also a longer runtime in general. But the other methods perform more or less the same. Another thing we can do, because we have this multi-discrete action space of only 12 actions, where the agent can effectively perform up to 3 actions in the same time step, we can assign a different color coding to them and then visualize how this distribution of actions that the agent prefers changes over the span of training during the sequence. So at the beginning of the task, it more or less starts out with a uniform distribution, and then it relatively quickly, because PadNet has had quite good performance, quickly manages to find a distribution that is what determine which are the actions that are preferable for having high returns on a given task. So we can see that different tasks potentially, these are not of course the the optimal distributions, we don't really know those, but due to the fact of PackNet having high performance, we can assume that these are useful actions to use on this given environment. But of course, we're more interested in the evaluation performance, not only the training one. So we can visualize how this action distribution changes or doesn't change for the initial task. So although we do continue training on future tasks, we can still see whether PackNet manages to remember the action distribution it learned for the first task. And we can indeed see that it stays more or less the same until the end of the sequence. And hence it also has a high performance as we saw previously. So similarly with the second task, again, it starts out more or less uniform, and the method gains access to learning the task, and it finds a good distribution, and it maintains that until the end of the sequence. And this continues until the end. So this is an extra notion that we can use to determine how well the policy is doing. Going further, we tried different alterations to the methods we had. So we tried some image augmentation methods because we learned from pixels, but we noticed that the shift and noise augmentations didn't really affect the performance much, whereas the applying random convolutions to the inputs was a bit too much and even made the performance worse rather than better. And we tried adding an LSTM encoder, and that completely hindered learning for a lot of methods in the continual learning setting. And then maybe more interestingly, so by default in our setting, we allowed multiple output heads. So if there are 8 tasks in the sequence, then our network, the actor network also has 8 output heads. So we always take the network outputs, the actor outputs from the correct output head. So in our setting, we made things a bit easier. The agent, first of all, knows which environment it's being trained on and which it's being evaluated on. And we also use the multiple output heads. So that makes things a bit easier, but we also add the settings where you can use a single output head or the agent doesn't know about which task it's being evaluated or trained on. These are just different continual learning formulations. So, but then we compared what if we just use a single output head and not allow multiple output heads. So then the problem becomes a bit harder because now for each task in the sequence, the actor has to output the action that it thinks the best through the same sort of output. And we can see that the methods that performed better in the main results, such as PackNet and calling stack, also have very low performance decrease if we use the single output head, whereas the regularization-based methods were more volatile towards that and have a higher performance loss. And then lastly, we observed that regularizing the critic is harmful for the regularization-based methods. Because when we try to regularize the weights from, our goal is not to forget previous tasks, then the question is, do we only regularize the critic or the actor or both? And it turned out that regularizing the critic is actually decreases performance. So we should only regularize the actor, as the regularization-based methods had a very high performance decrease with that. So going further, it's known that neural networks lose their plasticity over time as they are continuously being trained on. This is coined as the loss of plasticity. So we also looked into whether we can observe this loss of plasticity in our training sequences. So what we did was we train just the soft actor critic method on the main sequence, and then we do it multiple times over and over again. So in total, it will train on 80 tasks. It's not evaluated on anything. We only care about the training performance, whether it's able to reach the same performance after each iteration of the sequence. So what we surprisingly see is that first, initially, during the first 5 iterations of training on the sequence, it does lose out on its peak performance that it's able to obtain. But then after roughly the fourth or fifth iteration of the sequence, the performance picks back up again, and it more or less reaches the same peak performance on each task as it did initially on the first iteration of the sequence. So effectively every spike here, if you take the top left one of the pitfall as an example, then every spike shows the training curve of the kth or nth iteration of the sequence, right? So we start with pitfall, we train the agent for, here it's 100,000 time steps, and then we plot the first spike, and then we continue training on the other tasks, and then we start over on the beginning of the sequence, and then we can plot the second spike and so forth. So notice that these graphs are not continuous, but they show on every iteration of the sequence this given task. And we did not really notice loss of plasticity in the whole. Of course, the question is, what if we now train it up for 20 or 30 repetitions? What would happen then? But again, well, this is for future work to determine, I guess. But it was an interesting observation. And then finally, because, well, not only do we want to analyze the performance and capabilities of the current methods, we also want to have a challenge for future methods for continual learning. So we take the main continual learning sequence and create a harder version of the environment, create a harder version for each of these environments that may include making the map larger, decreasing the items there, so it creates more sparse rewards or different types of complexities. And then we take the two best performing methods and we compare them on these harder environments. We compare their performance on the hard environments and the original ones, and we can see that there's like a big performance gap there. So we're safe to say that these more challenging environments are a harder problem, present a greater challenge for these methods, and the current ones are not even close to be able to solve them. So with that, I can wrap up the continual learning project, and then perhaps it's another quick round of questions before I continue with the last one.
Yeah, I think it would be nice time for questions. We have a hand up from Sam.
Okay, so I actually have a few questions, but maybe we don't do all of them, well, depending on time. So I was wondering, you said there is two types of transfer, and I'm not sure I caught that. Like there's the forward transfer and another type. Could you just like re-explain it quickly?
See how fast my finger is to get back to the that slides, so it's a bit easier. Yeah, so forward transfer, when we have a sequence here of tasks where we have access to a task, we learn it, we lose that access, we start learning a new task. So when we talk about forward transfer, perhaps we have learned something from these initial tasks that makes us capable of learning the next task faster, right? So for instance, within the Doom environment, with the Lego blocks, perhaps you know how to create basic structures. You've learned the capability to create some basic structures, and then you can already use that knowledge to learn the new task faster and perhaps more efficiently. So that's forward transfer. And backward transfer is if we've learned a sequence of tasks and now we are able to have increased evaluation performance on one of the initial tasks that we already learned. So take, for instance, I've never played squash, but I go play tennis for a few years, then probably if you put me on a squash court and give me a squash racket, I will have reasonable performance, although I've never played squash, right? So that would be forward transfer. And perhaps if I learned to play, so I play tennis for a couple of months, but then I go play badminton for next several months. And perhaps while playing badminton, I improve my footwork or I improve some other necessary skills that make me better at tennis, although I was never practicing tennis during those last few months. So this is how you can have the knowledge or skill transfer back and forward without then having access to certain tasks, so to say.
Oh, I see. Yeah, yeah, that makes sense. And you said that like basically the architecture you use is that you have like different heads for each task, for both for the actor and for the critic.
Only the actor. The
Only the
critic
actor.
still has the single output head, just gives a single value.
And do you share the same like representation between the actor and the critic, or are they different?
Yes, the convolutional head is the same, and then the actor and critic are separate, so that they share the same backbone, if that's what you were asking.
Okay, so basically in forward transfer you would have this shared representation, and you expect that like the representation is going to, I mean, between tasks, because you have different output heads for the actor, and that representation should be useful to go from one task to the other.
Right, exactly. Yeah, that's a fair point. So perhaps the premise is that with the single head architecture, the forward transfer can be even increased because it's using the full network architecture. It's sort of reusing that for the next task. Whereas with the multi-head architecture, it's only using the backbone plus the few extra fully connected layers before the output head, technically. So it's the same network that's being reused and trained on.
I see. And you mentioned you're doing some critic regularization. Is it a particular what sort of regularization do you do on the critic?
Yeah, so this depends. This is contingent on the continual learning method itself. So it mainly applies for, well, only these continual learning methods that do impose some sort of regularization. So we can see that L2 and the memory aware synapses, they have different types of regularizations that they apply to not forget the weights.
Okay, yeah, that's interesting. In a zero-shot generalization, in my own work, we also see that like it's actually can be helpful to have like a sort of overfit critic, so you don't regularize it, as long as like you keep them like separate, like the actor and the critic, because like you can like predict more accurately the value of each level or each task this way.
Yeah, that makes sense. That's interesting. Yeah.
Okay, thanks.
Yeah, thanks.
Cool. I also have one, I guess, quick question. How important is the order of the tasks? Because it feels like, I guess, especially things like, I guess even like forward and backward transfer, the order of the tasks would be quite important.
Yeah, that's true.
Did you play around with that, or did you use a fixed order that made sense?
So we used the fixed order because although the Doom environment is still not that computationally expensive to run, when it comes to continual learning, we have to train on all 8 tasks. We also tried 16 tasks to combine both of these. So it still takes a lot of time. And because of that, we weren't really able to do the random task sequence setting, because having a random task sequence means that if we really want to compare different methods, we need to have 50 or 100 or more runs through this sequence, because that different order might cause very different performance in terms of either forgetting or transfer. The question is, how similar are the environments that are maybe close to each other? That might matter a lot. So we just heuristically chose an arbitrary sequence where so for instance, as I showed, the tasks that interfere with each other, we put them maybe either more closer to each other, it doesn't really matter. But yeah, we try to spread it out a bit to have not two similar environments next to each other. But ideally, yes, we do have, for using the benchmark, we do have an option to just use the random sequence every time. But then it would be a bit more costly, and you would need more runs and iterations to have meaningful, fair results across the methods.
Cool. Yeah, that makes sense. Thanks. We have another hand. Yeah, let's maybe make that the last question, and then we can do questions at the end as well. Gerard, go ahead.
I cannot hear you. At least I cannot hear you.
Yeah, sound is, can't hear you. Maybe type the question in the chat.
So I guess you guys still can't hear me?
Yeah.
No, we can hear you now.
Okay, I see. So let me try to be quick. I probably missed this, but like in this like egocentric, right? There's some elements of partial observability here. I see you mentioned that you tried LSTM versus no LSTM, and LSTM just made everything trash. So like I guess you were training all of these things, just using the CNN, and probably the diversity of the environments made it like fully observable. Like you
What was the last part about the fully observable?
So like you just use CNNs and you didn't really do anything special for partial observability. It just worked with the CNN and no frame stacking or anything like that.
We did use frame stacking.
Okay.
We used the canonical nature CNN network from the old
From the
Atari paper,
GQN paper.
essentially. Yeah, exactly that one. And
Okay.
you did use frame stacking of 4 frames, but yeah, the LSTM didn't really somehow made the evaluation performance a lot worse. So
I
we
see.
didn't use anything fancy apart from the continual learning methods themselves, because often they might apply some extra, because there are methods that more of the architecture-based methods, they might add another layer for each task, for instance. So that really, the network architecture might depend more on the method itself at hand.
Okay. Cool.
Yeah.
Thanks.
Yeah, thanks. Okay, I will go on then with the final chapter of the talk, which is safe reinforcement learning. And well, as you already know the drill, first a few words about what we care about in SafeRL. So imagine we want to build a high tower, but if we do this very carelessly and recklessly, we might indeed end up with a high tower, but it might be very unstable and therefore unsafe. And we might have to start over again. And we won't have a good final objective in our with the policy we had. So if instead we approach it with a more safe policy and we start out by making a lower tower, but ensuring it is safe, then perhaps we can go from there on and building a higher tower and having it both as high as we want, but also safe. So it's kind of a constraint setting. So unsurprisingly, perhaps we then propose the safe reinforcement learning benchmark, once again, based on the Doom environment. And this time the goal is to maximize the reward as normal, but now each of these environments has these predefined safety thresholds, also known as the cost budget, that the agent should not exceed. So it's like a constrained optimization problem, effectively, trying to maximize the reward while minimizing the cost, or at least keeping it under the safety threshold. And we evaluate these safe RL methods, all based on PPO to ensure fair comparison. And one of them is just normal PPO, which more or less sets an upper bound for reward and cost, which you can also see in the main results, as the blue curve generally is always the highest because PPO doesn't care about the cost, so it always maximizes the reward in a greedy fashion, and often setting the upper bound for cost as well. Whereas the other methods, the PPO, P-Lagrangian, and P3O are generally the better performing ones. So to interpret these graphs, we always have a cost threshold, which is shown by this by the dotted lines. And then what we care about is keeping the cost curve under this threshold and then having the reward as high as possible. So going further, here we can ask, what does the location or the movement of the agent tell us about its performance or its policy in general? Because we have a navigable environment, we can then try to determine how we can analyze or inhibit or estimate what the performance of the agent is given its movement. So if we take one of the tasks as an example, so in this task, the agent has to pick up these health vials that you see on the bottom left corner, and there are also other health items, and it has to avoid all of the other items. So it's seemingly simple enough. So the vials grant a reward and the other items grant the cost. And we can visualize this map on a top-down view in this 2D fashion. And then we can plot the evolution of the heat map across the training period of 100 million time steps. So we can see that with the case of PPO, it's quite straightforward. It shortly random, perhaps we can look at the curves for the reward and cost, and they're pretty generic. And to better analyze what it's doing, we can perhaps divide the training into stages. So with PPO, as I said, it's relatively straightforward as it starts by randomly exploring and then just finding a greedy strategy and maximizing the reward without caring about the cost because it doesn't know anything about the costs. But now if we compare that to safe reinforcement learning method, then we can observe a very different pattern of its movement. Particularly at the beginning, it also has quite a lot of movement, but then shortly afterwards, it has a very conservative policy, and the map, there's not a lot of movement, and he's staying at certain positions. And if we look at the training curves, we can see that there's a correlation there. And we can analyze this if we, again, divide the sequence into different stages. So it starts out the same by randomly exploring, and then using a greedy strategy to maximize its rewards, but it notices that the costs also goes up. So then, according to the nature of the method with PID Lagrangian, it tries to reduce the cost to meet the safety budget or the cost threshold. And it does that by sacrificing reward. So once it has reached the cost threshold, this is effectively on the heat map, which you see the very the period where it does not move a lot. It tries to stay under the cost threshold and keep on increasing, adjusting its policy to find rewards and optimize for its returns. And then finally, when the heat map gets very green, is when it further refines its strategy, and now it's more free to navigate the environment, and it knows what to avoid and what to collect. So it manages to keep a low cost while having a high reward. We also have difficulty levels in the benchmark, and I can, with the example of perhaps this task, I could give an example how we introduce these difficulty levels. So in this particular environment, the agent has to find the weapons in the ground and then deliver them to the starting zone. And it only is rewarded once it manages to deliver the weapons, not when it picks them up. So it gets a reward for that. But the catch is that it has a carrying capacity, which it doesn't really know about, which is set to 1.0 in this experiment. And every weapon or every item that it can pick up is associated with a weight and a reward. So the higher the weight, the higher the reward. So because of the carrying capacity, the moment it exceeds it, it starts getting a cost. So it has to find a good strategy to balance out which weapons to pick up and when to come back to the starting zone to have maximal return in the shortest amount of time. And when with higher levels, we can introduce like a more complex terrain that the agent has a harder time navigating, or even obstacles that inhibit its movement, or at these decoy items that add weight, as you can also see in the bottom table, but they don't grant any reward. But the agent doesn't know that when it picks them up, because then the items don't grant any reward when being picked up, not even the weapons. And then we add these acid pits where the agent might fall if it doesn't look out for its step, and then the episode restarts and it gets a higher cost. And if we look at the heat map evolution, then we can notice that with the higher levels, the agent is not that capable of exploring the full environment. It tends to stay close to the starting zone. As the environment gets more difficult to navigate, it's preferring, if there are any weapons that spawn closer, it's going to prefer them. That sort of shows a notion of complexity. And this is with the PPO-Lagrangian method. A different method, the Sauté one, did not perform that well in this environment. And we can also see this from the heat maps, which indicate a very sporadic and unpredictable behavior. So we can often, if we have a good baseline for what is a good evolution of the heat map or what it generally needs to be doing, then without knowing the reward or cost, we can already assume from this heat map evolution what the policy or what the behavior of the agent might be. So another thing with these difficulty levels, taking this task as an example, where the agent has to shoot the enemies but not harm the neutral units. So it has to have good aim, and it gets a reward for shooting, for correctly targeting the associated enemy units, and it gets a cost when harming the neutral ones. And with higher levels, we bring the agent further back from the targets, and the enemies become faster, and there's fewer of them, and there are more neutral units. So it's a much harder task. And we can notice that directly training on the level 3 environment can lead to very conservative behavior, because now the agent doesn't really take many risks and only shoots one rocket when there's not even anyone nearby. So then we can think, can we somehow have a better policy by leveraging the lower level environments? So in particular, we no longer just directly train 300 million time steps on the level 3 environment, but instead we train 100 million on each consecutively. And so we have our curriculum agent. And then if we compare them, we can definitely see that the curriculum one is more perhaps prone to risk-taking and shooting the rockets and even targeting the enemies appropriately. And if we look at the results, then indeed we see like roughly a 30% increase of reward, while the costs are more or less similar. And we also tried this on one of the previous environments I talked about, where we had a 3-fold increase on the level 3 evaluation performance, while the cost is still under the cost threshold, which is 5 in this case. So we can have a sort of implicit curriculum across these difficulty levels. Then, because I mentioned there's a predefined cost threshold, well, this is arbitrarily defined because in most problem settings, we don't really know what the cost is. So we just set an arbitrary value as a cost budget. But what we can do is explore how adjusting this cost budget, what this does to the performance. So the default values are 5 and 50, respectively here. So a tighter bound, which is indicated by the darker shades of color, generally the PPO-Lagrangian method is able to very closely adhere to these safety bounds, but then again, it almost always gets a lower reward because of that. So it always has to sacrifice some reward to reach the lower safety bound, which are 25 and 2.5 here. And similarly, if we loosen the safety bound, we allow the agent to make more mistakes and incur more costs, then the method can leverage that and still adhere to the looser safety bound, the 75 and 7.5, but then have higher reward, which are the curves with the lighter colors. And there are a few exceptions here, but generally this applies. So we can see that there's a direct cost and reward trade-off from the environments, and it's implicit. So this is useful for when we define what kind of a budget do we want to have in a particular problem setting. Okay.
Sorry to interrupt, just giving you a heads up. We are on the hour mark, but yeah, happy to stay a bit longer.
Right, thanks.
Have discussions and stuff, but just giving you a heads up.
Yeah, thanks. I'll quickly wrap up. So here we compared the benchmark with the performance of it on Safety Gymnasium, which is one of the more popular SafeRL environment suites out there. So we can see a magnitudinal increase in terms of both how many environment frames it's able to simulate and how many policy updates we are able to do in like a single GPU setting in that time. And yeah, here I just thought if I have more time, I'll explain a few more tasks and show how the heat maps evolve. But because there's a lack of time, I'll skip this for now and give the floor to you guys again if you have any questions to ask. And with that, I would also like to thank you all for coming and listening, and hope perhaps, although I might have disappointed the ones who came for a more involved and mathematically involved talk, it's still mildly interesting, and I hope you enjoyed. Thanks.
Thanks for the talk. Yeah, it was great, and it was really nice seeing sort of the transition across all these environments and seeing you explore these different questions. But yeah, thanks for the talk. It was a great talk. What I will do now is stop the recording, but we can still stay and ask questions and just have discussions until people want to